Okay, welcome everybody to this month's installment of the Chalmers AI for Science seminar. Today we have Kirill Neklyudov, who is joining us from the University of Montreal and MILA. So Kirill is interested in generative modeling and sampling techniques, specifically with applications in the sciences. And he's done his PhD in the Higher School of Economics in Moscow, Russia. After that, he moved on to Amsterdam to do a postdoc with Max Welling, and then he went to the Vector Institute to do another postdoc. And now, since summer last year, you've been in Montreal. So we're very happy to have you here, and thank you for coming and for all the nice discussions throughout the day. And we're looking forward to your talk. Welcome.
Thank you so much, Simon. Thank you for the introduction. Yeah, I'm happy to be here and talk about our recent works, which were on controlling diffusion models at inference time. And so I put a lot of occasions in the slides, and I just want to say a small forward for this, because when I was a student, I used to think that I have to rederive immediately everything that I see on the slide and check all the equations. And I think I've been losing kind of a big picture sometimes. But you should treat the equations in this talk in particular as kind of a texture that isn't half of a big picture, right? So you can't kind of draw a painting without making the texture, but you can. But the painting is not about the texture. So this talk is not about the particular equations. And if you feel sometimes lost, don't be afraid. Just relax and try to enjoy and follow the concepts and ideas. I structured my talk as follows. I want to start with the motivation for controlling the inference processes. And I already chatted with a lot of you, and I see that this is quite relevant to your community. So I don't think we're going to have problems in here. And then I'll move to the first work, which we call Superposition of Diffusion Models. And for both works, I divide it's in two stages. First stage is the mathematical tools and the abstract concepts that we're using to derive the result. And the second is the empirical study, the application. So the first work is about the superposition of diffusion models and the eta density estimator. This is a way to estimate the density efficiently once you do the inference of the diffusion model. And the second work is we call Feynman-Kac Correctors for annealing products in classifier-free guidance. And here we will talk first about Feynman-Kac formula, sequential Monte Carlo, and then we'll apply to generating molecules, generating images, and sampling from the Boltzmann density. All right, let's start with the motivation, with the outline. That's a common picture just to introduce the notation, what we're going to talk about. We're going to talk a lot about the diffusion models. So in diffusion models and in general in generative modeling, we are interested in doing the noising process during the training when we go from the existing data to some simple prior noise distribution. And this is we describe by this stochastic differential equation that applies just noise to the existing data. And at the inference process, we usually write down this equation to kind of reverse the process, right? To sample from something that is like data, starting from some simple noise distribution. I would argue that for scientific discovery and for generative modeling for scientific discovery should ask different questions. Namely, let's say that these purple blob describes some samples with property A, and this purple blob describes some samples with property B. And this little tiny orange dot in between describes some very interesting samples that like lives on the border of these blobs and has both properties, A and B. Or, for example, we're interested in the very center of this Gaussian, which can be like the best sample or like a reference sample with property B. And the question that we can ask is, how do we do inference? So we actually, instead of just sampling from the training data, we generate something interesting, unique, rare. In other words, we're doing scientific discoveries. The examples that I'm going to consider here, because you can define this like scientific discovery informally in many different ways, and we have to like to do some propose some method. We have to be precise with our wording. So I'm gonna like just describe several examples that we consider in this talk. We start with here I'm just like illustrating it on Gaussians, but of course we're gonna consider many different examples. Let's say you have two models. One is trained on trained data A and another on trained data B. And if you just average the outputs of the models, if you just like add the scores, for example, you will generate something in between which is not very interpretable. Instead, we first ask the question, how can we sample from the mixture of densities? It's kind of like a logical OR, right? So either sample from model A or sample from model B. So we have to be able to, if we generate several modalities, we want to be able to get a model that samples from both modalities out of two models. And then we can also wonder, how do we sample from equal densities? Some space where the density or probability under both distribution is the same. If you think about the Gaussians, it's just like the points in between these Gaussians, right? That has the same distance to the center of Gaussians. That's where it's presented. And this we're going to treat as another kind of logical AND. Because of the reasons I'm going to show later, how it works for images and how it works for molecules. This is the first paper. And the another application might be, we have some target distribution, and we train a model to sample from this target distribution, but then we want to change the temperature. For example, we trained on higher temperature, and we want to generate samples from a lower temperature. Another application might be the product of the densities. So this is another logical AND. A lot of people like interpret this as a logical AND, but the logical operations have kind of like informal interpretation. The main thing here is the mathematical formulation. What do we want to sample from? And finally, we also consider geometric average of densities, where we have kind of like a product of densities, but we take them with different temperatures, 1 minus beta and beta. So now, with these goals in mind of like being able to like do some mathematical operations with the densities we are sampling from, we head off to the first work, which is the superposition of diffusion models. For the mixture of densities, we actually like it's not that difficult to write down. We consider different diffusion processes. We assume that we know these vector fields ui at any moment t, and these densities qi or t, they're also they're not known, but these are the marginals of the diffusion process. So we know these diffusion processes in some sense. We can model them. How can we combine the mixture? So how can we define a diffusion process that samples from the just arithmetic average or the mixture of densities? What should be the vector field ut of x that samples from these densities? The good news are that the analytic solution for this vector field we have in the closed form. So we just have to take the vector field of ith model and weight it proportionally to the density of ith model. The bad news are that the density QTI is not known during the inference process, because we usually just have we follow this reverse SD, right, with the score and the drift, etc., but we don't have access to the density. So yes, this is the density of the IF model, which is not known. But we know usually nabla log QTI. So the natural question is then, how can we estimate these densities? And you can ask these questions to different types of inference. First type of inference is you simulate an ODE, and this is just some vector field. Let's say we know it, and we simulate this ODE to sample from our model, and another for SDs. So for ODEs, it's pretty straightforward. We simulate the ODE that follows this continuity equation. So it samples from all these marginals, and we can just track this full-time derivative. So the density changes, right, on the left in here, and also the coordinate changes. So there are like two different sources for the change of time. This is the change of density, and this is the change of the state. Then we can use our continuity equation from the top right and rewrite our equations like this. And this, the bad news, we have to estimate the divergence of our vector field. So we have an additional backpropagation step. But the good news is that we usually know this part. We usually know the score when we train a diffusion model. So the vector fields in here, we all know, and we can track down the divergence for any vector field UT. That's the main point. Not only for the vector fields for the reverse process. It allows us to control things. But let's look at what happens with SDs. With SDs, we have this additional term, which is the Wiener process, and this corresponds to the noise that we add to every single step. The full-time derivative for this, it looks very similar in the beginning. It's also the change of density, and that's the change of the state, right? Because our density changes in time, and xt also depends on time, so we have to account for the change of the state. There is another term in here that appears because of the noise. And it appears due to the Ito lemma. And the intuition for this is that this noise, dWt, it has kind of a scale of square root of dt. So once we do the Taylor expansion, we do all these like accounting and algebra, and we have to take into account kind of the second derivative of log density that appears in here. But so the second derivative for everyone, like in computational methods, kind of like a red flag, because like it's very expensive to estimate. But let's not judge this quickly, and let's see what's this partial time derivative of log density. We can remember that this time derivative is actually derived from the diffusion process, because during training, we apply this noising process as a diffusion, right? So we have this equation for the noising process in here. And once we inverse time to go into the opposite direction, we get this partial differential equation. Once we do all the algebra with like taking logarithms, etc., we get this equation at the bottom for the term, for the partial derivative. And namely, like in particular, these terms cancel out, and we get the result. So this was like a glimpse into like what you need to do to derive and like prove all of this. But it was a little bit fast, but let's take a bit of more time to discuss the result. This is the eta density estimator, and it tells us the following. So first of all, you can put in here any vector field. It's not necessarily the vector field that generates your samples. It can be any other vector field. The diffusion coefficient you're not allowed to touch. You have to use the diffusion coefficient that you use during training because we need to cancel out these Laplacian terms and avoid the second derivative. The scores, we assume that we know during inference. This is a good assumption because machine learning models are trained to like approximate these scores. And this part, which also looks like a scary thing because it's a divergence, so it's like a lot of derivatives in it. This part doesn't matter because the drift ft of xt usually doesn't matter. It's some like linear scaling, and the divergence of this linear scaling is just a constant. As a result, for like image experiments, we can run it like 5 times faster than like OD with backpropagation and save a lot of memory. So I would also say that this doesn't require any extra computations besides the forward pass, and you get some information about the density of your process for free, which is pretty nice. You can use it in many different ways. So this is a principled approach in the sense that like it doesn't matter how exactly you model the scores, which architecture you're using, and like what data you're using, et cetera, et cetera. You can use it applied for any number of models. The caveat in here is that there is an assumption that the scores are very well trained. So you can't apply during training, right? If your model is like under-trained, you should not expect very good accuracy from this thing. All right, so the second thing is the end, and this is like sampling from equal densities. So think about this, like you have two distributions, and they're like the green distribution and the purple one, and these lines in between are actually the lines for the space where the density under both model is equal. So in some sense, the point on this line is like equally probable to be a green point or a purple point. If you were to like build a classifier, right? It would be like somewhere you can distinguish classes. You have your current sample, and the idea for equal density is like one model pushes to generate green samples, another model pushes to generate purple samples. And we want to kind of like balance them to stay on this line in between models where we can't distinguish classes. And we want to proceed like this. Always stay on this kind of like hypersurface or like hyperplane. What we do is we combine these vector fields from different models, UTI, just as a linear combination with kappa I. And we assume that the current densities are equal. So we assume that like sample in the beginning has the same density, or like at every iteration, we assume that the sample has the same density under both models. So the question is like, how do we guarantee that at the next time step, we preserve this equality? So this is nothing very fancy and like nothing very complicated. We just do like Taylor expansion, and we see that, okay, now if the change of density is the same, then it's approximately up to little o of dt, it's going to be approximately the same. So we have to equate this change of densities. And this can be done just using the eta density estimator, because we know how the density is going to change. So we can control, we just solve like a linear system of equations. We control the change of density. We find this such kappa that the change of density is the same. So this is how normal inference looks like. We have this like minus drift plus some vector field ut, which is like the score, et cetera, et cetera. And then for or we evaluate these kappas or the coefficients in one way, dependent on the density. For and we evaluate them in another way. We plug them in here. And in the end, we also have to update the density, and that's what we can kind of decide based on the density. So the empirical study for this, I'm going to start with the CFAR10, with the very simple case where what we try to, the very first thing we tried. We can split CFAR into 5 non-intersecting data sets, 5 labels and 5 labels. And then we train a diffusion model on each of the halves. We measure a bunch of metrics, but in total, what we see that both model A and model B, they don't perform well, of course, because they're trained just on the half of the data set. If we train the joint model, we see that it's much better, of course. So then what we do is we randomly select model A or model B and sample from either of them, and we see that the mixture performs very close to the total model, right? So this is the different color of Gaussians, and we cover them with orange Gaussians. Now we run our method that estimates the density and gets the vector field, and it gets the same performance as this model A or B. But the cool part is that we know the vector field. So now we can distill this both model, even without knowing the data set. We can distill this model into a new model, which we don't need to store. So we don't need to store 2 models. We don't need to throw the coin. And we can even tweak this model a little bit with some hyperparameters and get better results in terms of this metric that tracks novelty, for example, and generates better results, which was quite surprising. But this is still a toy task. To get it to on a more complicated task, we went to Hugging Face to do experiment with stable diffusion, and we asked stable diffusion V1.4 to generate a flamingo that looks like a candy cane. And this is one of the generations that you get that looks like flamingo, except 3 legs, but not like a candy cane. And you can run multiple different prompts. So here, for all the images, we took 2 different prompts. You can actually see candy cane now here and guess that it's flamingo. But for some images, for here, you just can see the donut. But actually, this is also a map. We asked donut that looks like a map or a map that looks like a donut. We tried both sides. We tried different prompts, et cetera, et cetera. And the map doesn't appear for the donut, for example. What it appears, it starts appearing if we just average the outputs. If we just kind of generate using one model, prompt it on donut, another model that prompted on map, and then they mix these outputs, and then the map is kind of starts looking like. But if we apply our method, we get the map that looks like a donut, I guess, or the vice versa. It's very hard to tell. We get many different things, so we now see both concepts clearly, and the generations are much better. We can, of course, measure this. We can measure this computationally in terms of clip, image reward, and also essentially assessing using LLMs. It's question answering with LLMs. And we get better metrics for image generation. And we can take it, it's SDXL and run it on SDXL and get much better pictures of 2 concepts. So what if we apply the same concept now, but for generating molecules? So here are the model that is prompted. One model is prompted, this molecule inhibits this enzyme, and another model, this model looks like a drug. And we track both responses drug likeness and enzyme inhibition. And these are kind of our baselines, right? We don't hope to generate drug likeness better than this or enzyme inhibition better than this. But what we hope is that we can generate a molecule that inhibits this enzyme and is a drug, right? So what we try to do it like first with joint prompting. These are the metrics that we get, and if we try to average the scores, we get different metrics. But the main thing is that once we do our method, we get the best metrics in terms of kind of like a product of these two properties. So we try to generate a molecule that both inhibits some enzyme and looks like a drug. It also like increases sometimes like the percentage of valid like in unique molecules compared to, for example, the joint prompting, which is also interesting. And these are the molecules with the scores with different models. I don't know how to interpret them, unfortunately. These are just to validate that we generate something reasonable. We can also change the task, right? We can inhibit two enzymes simultaneously, and we can get, this is the molecule. What we can get, it's like either minimum of these two scores or the product of properties. We beat the baselines in terms of joint prompting and just averaging of outputs. As a summary, we can do this mixture of models if we, for continual training or decentralized training, when we train different parts of the model and then we distill into one. We can also generate samples with like several properties for images, or maybe study the density model of the learned model. We can customize it in general, like now we have the information about the density of the generated sample. So in some sense, it's like in autoregressive models, right? We have the information of the probability of the generated sample. And now we get the same feature in diffusion models. We can make actions and control based on this additional information on the density. And we just can repurpose generative models based on this in many different ways, combining properties and guiding somehow. This is the paper that we're going to present on ICLR very soon. These are my collaborators. And yeah, I think now we can go to the second paper. Perfect. The second paper, the tools are going to be different because to get the product of distribution. So I said like the end in the eta density estimator was this control of the density, but you probably can do some important sampling with the eta density estimator. But what we found is that there are other tools here to, like, for example, simulate the product. These tools are complementary, so I have to talk about them. And I would like to start in general, like, there are different tools for simulating PDEs on a computer. In the realm of PDEs, we can simulate for example, the continuity equation we simulate just by moving samples in space. For diffusion equation, we add some noise to the samples, right? And there is a third equation, which is going to be kind of like the main role in this work, is the reweighting equation. It's the equation that takes a sample. It doesn't move it around. It doesn't add noise. It doesn't change the coordinates. What it does, it assigns a different number to it and treats it as an importance weight. So it's like now samples are not equal. They have weights. And in general, if we combine all these equations, you're going to have the Feynman-Kac partial differential equation in the most general form, which is simulated like this. It's the stochastic differential equation where you also keep track of the weights. These weights are next to every single sample. Every single sample has a personal weight, and we update these weights. So you've seen these equations before, but without the last term. So in the orange boxes, these are just like Fokker-Planck equation and the corresponding stochastic differential equation. But the last term and the corresponding weights, these are like new players here. This is the reweighting equation, these guys. To get some intuition, I want to describe this picture from like sequential Monte Carlo literature. You can think about all the samples as these like little yellow points in here. And at every step, what we do, we move them in space and we update the weights. And once we update the weights, this yellow point, for example, became very big. You see, like it's an important point for some reason. We increase the weight, and after this, we can do the resampling step. The resampling step is the following. Instead of simulating single particle with a lot of weight, we can split this sample into 3 samples, like proportionally to the weight, right? And then simulate them separately. And this allows to reduce the variance, because you don't want to end up with like one particle that has a lot of weights. You want to cover your space. In some sense, you can think about this as an evolutionary algorithm. You assign some importance to the particles and you keep the promising ones, but at some point you want to like branch out and explore other regions and just remove the unimportant ones, right? The crucial kind of like part of this work is based on the following insight. If we have a simulation scheme, let's say we simulate an OD that looks like this. This is what we oftentimes do in the inference of the diffusion models. We take the score of some density and then we propagate our particle. And we can write down the corresponding PDE. This is the continuity equation, because we just described that like ODs, continuity equation, right? Then we can do some algebra. We can find another equation in here. This is the diffusion equation. And we can realize that another simulation corresponds to the same equation. So the insight is the following. For one PDE, we can write down, like oftentimes infinitely many ways of simulating this PDE. And this what allows us to, it's kind of like different interpretations of the same law, I know. Like on a computer, we don't care much about like, so in physical world, of course, like if something, we can simulate stochasticity, right, differently, right? But on a computer, we can decide what we upweight, what we move, how we add stochasticity, and so on and so forth. And with this insight, we can do all these things. We can anneal the density, we can do the product of the distribution, which can be another interpretation of AND, and we can also derive the geometric average of the densities. I'm gonna describe the approach in kind of like wide strokes. It's let's say you have 2 pre-trained diffusion models. That usually means that minus ft of x, this is kind of like not a very important thing, but because it's just like a linear drift. But what we know is like this scores, right? So nabla log qt, this is what we train in diffusion. And we want to like modify the inference to sample from this geometric average. Because we want to sample from the geometric average at the last moment of time. So this is an important detail. The detail is that we want the last thing. We want to sample from the t capital, right? The last time point. But what we change our process for all marginals. For all distributions in between, during the generations, we change these densities like this. And this is what we can simulate, and this is what we want to simulate. So what we do is we are, okay, let's write down what we want to simulate and take a time derivative. And it's going to be like an expression like this, and we're like, okay, this is so far so good. We can simulate using this. But if you do like all the algebra and all the accounting, you will find out that there are like a bunch of other terms in these partial differential equations that just don't fit into the Fokker-Planck equation. So if you just take the time derivative of what you want, you see that this can't be simulated just by rescaling the scores, adding the scores, manipulating with this. Like classifier-free guidance in that sense, like, is a trick. It's not a proper way to sample from the geometric average of distributions. Because if you simply change the score, it doesn't mean that the marginals you're sampling from are going to change accordingly. So we can interpret these terms as weights. And this is what allows us to like go back and forth and like write down different SDs, write down different schemes. This is like the main tool. We can change the interpretations of different parts of PDEs as we like, as convenient for us for simulation on a computer. So for empirical study, we take different problems, and for different problem, we derive its own scheme. We start with the classifier-free guidance. The classifier-free guidance is usually like the motivation is that we want to sample from the geometric average where between the unconditional distribution, Q1, that is conditioned kind of on an empty set, and Qt that is conditioned on some Y. And Y is like class label, let's say, but we're going to see like what it can be. Then we have the following weighted SD. So dxt is the SD that we simulate. That's how we move the samples. In d log wt is this equation that changes weights. So the weights are greater than 0 for high beta that we usually set in classifier-free guidance. And the intuition is that we set large weights for opposite directions. So if the directions are different of the like conditional score and unconditional model, these are like outputs of the model conditioned on different labels. Then this sample is probably important. If this sample is very different in some sense from general samples, that's how you can interpret this. So that's what I was saying about the classifier-free guidance. The common intuition doesn't hold in the sense that this equation dxt is not enough for a simulation, and you can verify it yourself by like going through this derivation of the PDE, but you'll find some other terms that have to be interpreted somehow. We interpret them as weights and simulate them as weights to get these marginals. These are the results for images. We just, because like classifier-free guidance is such a popular technique for generation, for image generation, we decided to try it out there. This is like stable diffusion Excel with different parameters, the batch size, and we see that we can get better kind of like adherence to the prompt. We did other experiments, and like we're gonna update the paper soon on other like pixel space models, and there we observed like improvement of metrics on like a large scale experiments. Here it's not a lot of images, but still like metrics improve. The product of diffusion models is the second application. Now, it's not the geometric average. We want sample from Q1 and Q2. So this is kind of like a logical end. We want a sample that complies with both labels, Y1 and Y2. So we have to do the following. We have to add the scores. And then what people have tried before, they add the scores and they say, OK, yes, mathematically, this doesn't hold. Like, you need these PDEs and so on and so forth. So why don't we, instead of simulating nabla log Q, like parameterizing with the neural network, we can parameterize log Q, and then we take nabla, right? Then we take the derivative. The problem with this is that it requires training a energy-based model, parameterizing Q. It has some computational instabilities. And another issue with this is that you'll have to do additional steps while you're integrating to do Monte Carlo in between. You have to do like Metropolis Hastings correction, and that's what they are doing. That's why they are training an energy-based model. So we simulate this weighted SDE, and here we use only scores. We don't need to use log Q. And large weights are for aligned directions. There is a nice intuition for this. You propagate your samples, and then if the outputs of the models agree, models are conditioned on different labels, but if the outputs of the models agree, then it's an important sample problem. You can prompt image models with different text. You can prompt molecule generation models with different like enzymes inhibition with different text, or you can prompt you can generate molecules from the models that take a 3D structure of a protein packet as a condition. So as a result, we focus on the 3D structure. That's kind of like more interesting for us because this is like a lock and key hypothesis that's I'm pretty sure you're all aware about. That we want to generate a molecule that kind of fits into the lock, and the goal is to generate molecules. What we test on our task is like generate the molecules that fit into two different pockets. One molecule that opens two locks, essentially. One key that opens two locks. So we test this on the molecule generation models, and we see that here we first, like as a baseline, like we take the target one pocket only, and we get this like score around -12, and this is probably what the best we can get, right? But then we do the average of scores and sum of scores in different baselines, try different things, and we see that we have to do this resampling technique. We have to do the scores, and then we get the best results for both protein pockets. And we reach like -11 for both protein pockets. But these results are not filtered for drug likeness, for the proxy for drug likeness for QED. But we can filter them, and we see that the difference is even like more drastic. We take the baselines, and we can't even reach like -10 scores for both protein pockets. But with our method, one is like -10 and another is -12. So these are for dual targets. And also, if we do it for different sizes of molecules, because we add the scores, when we add the scores, we have to fix kind of the size of the molecule. So we do a sweep over the sizes, and we see an improvement over different sizes. And the last thing is the inference time annealing that I mentioned. Here, the idea is that we can control the temperature of our marginals. So why? The first question. Because, for example, we would like during training to train on a marginal with a high temperature, because high temperature means easy target, right? We kind of like add, we smooth the target significantly. But during inference, we want to do annealing. And if we train for like with the temperature 1/beta, we do annealing with beta, and we get beta/beta, so we get back our target distribution that we have to sample from. So annealing at inference, we reach the target. The target score looks like this. You can just scale with beta. You can scale your nabla log QT, the score. Or you can actually like do this algebraic kind of game and start looking for. I said like we have one PDE, we have many interpretations of this PDE, many simulations. So what we did is like we were like looking for different ways to simulate this, and we found like some other interpretations in more and more. And we started this equation as well. So here you change your scale in here, but you also change your noise. It's like less of a guidance, but less of a noise as well. The weighting scheme is the same though for all the equations. You just scale proportionally to beta and nabla log qt. And these are the results. So we just like said, okay, if it works for like it should work for Gaussians when we know all the scores. Like because here we rely on the knowledge of the score. Let's try it for Gaussians where we can evaluate the scores kind of like analytically. And we start with this kind of noisy distribution. It looks more noisy because it's a higher temperature. And this is what we want to sample. And then we compare essentially with this Feynman-Kac corrector without Feynman-Kac corrector. And Feynman-Kac corrector, you can think about these weights, additional weights that we are keeping tracking of. And like this is the reminder that we found in the PDEs and we are now accounting for. And for any SDE, once you add Feynman-Kac corrector, you for example, in here, you almost miss some modes. Some are completely missed, but here we recover them. And the same, here we don't recover all of them, but we do much better than without the Feynman-Kac corrector. So we said, great. Now we can take a diffusion-based sampler. We took them as one of the popular choices for a diffusion-based sampler. We do the following. We apply our intuition. We train them on higher temperature. We kind of saying like, okay, this task, you can solve it. It's quite easy. Lennard-Jones potential with temperature 2. But that once we do the inference, once we do the sampling, we now turn on our scheme and we sample from a much lower temperature. And here on the plot, you can see how much lower you can go. The answer, of course, is that like you can't go like super low, because the intuition for this is here. Because once you increase beta, the variance increases of the weights. But you can affiliate it with the resampling partially, but you can't go like from uniform distribution to like global maximum of this distribution. That would be infeasible, of course. But you can go pretty far. And what's most interesting, you can do much better than the same model, but trained immediately on the target distribution. So it makes total sense. So instead of like training your model on the target distribution, you can actually kind of pretend that your target is much easier, train it there, and then change your target to a lower temperature and actually simulate more complicated target. So I think this is kind of the best insight from this experiment that we got. We do the same comparison then in terms of these like histogram. These are the distributions of energies, and we see that like it's much lower. So because it's hard to like there is no kind of like a single benchmark in MCMC, so we generate a lot of samples, and then we track different metrics, and we see that here we are much closer to the target distribution, which is like in green. This is the histogram in green, and the yellow is the histogram that we generated, and purple is the target was sampled directly at the lower temperature. So in some other metrics, it's also much better. So as a summary, this is a framework for manipulating the density during inference. Different things, annealing, product, geometric divergence, you can derive many other stuff. This is like many different simulations, many different interpretations. if you're more familiar with sequential Monte Carlo literature, you can think about this as deriving the transition kernel, but from the continuous time perspective, and doing it like pretty much for free. Just, I mean, for free because it's like monotonous, you know, like derivatives and like moving parts of partial differential equations. And you can apply it to, like, you can add like reward to your densities. You can do classifier-based guidance. If you have a good classifier, if you have some other model in mind, you can play around with this. The trick here is that assumes the exact scores, right? Once again, as previously, as the eta density estimator makes a very important assumption that the scores are very well trained. But at the same time, this is what we need, because if we want to avoid energy-based models training, that's what we have to assume. And the message that I would like to highlight here is that this is all because of this reweighting equation and change of a lot of play with the change of the interpretation. We have a PDE, but we don't know how to simulate it. There are like multiple different ways. We can always look into this and get something out of this, of the change of the interpretation. This is the paper that I did with my great collaborators. Like, everyone has like their own expertise, and I think it would be impossible with like any of these co-authors, because there is a unique contribution from every of these co-authors. Yeah. And that's the end of the presentation. I'm happy to hear your questions. Yeah. Yeah.
Can I ask about, you showed two different models for kind of molecular optimization in a way, when you have two different properties. And I was curious there, I mean, one was the SuperDiff and the other one you showed later for the like binding pockets.
Yeah.
Have you compared the like the best molecules that you get with your sampling approach to the best molecules that would be present in the training sets for those individual like generative models, like those that would be at the Pareto front essentially? Are those that your model is generative?
That's actually a very good experiment. We haven't compared to the, like, because our idea is like, okay, we have a generative model, we want to repurpose it, we don't train anything else, we just like modify the inference time, but we haven't like checked for really generating something novel. I think that would be very interesting to try. Yeah, and like add to the experiments. Yeah, I'll tell Marta to, I'll pitch Marta this this experiment. She'll be excited. Yeah, but this is actually very interesting to see. Yeah.
I take one in the meantime. So you say, I didn't quite get this in the, so for the reweighting, you have to do this resampling step, right? So essentially, in the sequential Monte Carlo, you're resampling according to the weights.
Yeah. So okay.
Propagate the forward, you get a new position, a new sample. The weight associated with each sample, then you do resampling of the samples according to their weights. And then you do propagate those resamples.
Exactly. This is exactly what's happening. So you, like, in theory, this step of resampling is not needed. In theory, you can just like keep on these weights until the end of the simulation and just kind of like do the importance weights, and that's what's happening. But in practice, to remove, because like if something like this appears where like one sample overtakes the weights, then your variance increases, right? Because you, like, the variance is smallest when the weights are all uniform and you're just like exploring in different regions. And that's why we introduced not we introduced, that's like a very common practice in sequential Monte Carlo literature. There are like common tools like systematic resampling, et cetera, and we use all of them just to, it's like a variance reduction trick for the inference, yeah.
Yeah, I was thinking like, how does this like translating to the, that you actually pick up more modes in this neural sampling scheme. But
Oh.
Expect this to actually like be a little bit more mode seeking. Maybe you can build some intuition of why that doesn't happen.
Why? So the mode seeking is resampling?
Yeah, I would expect the resampling because you would depending on what the weights exactly reflect, right?
Mm-hmm. So the thing is that the resampling, I think, allows for more exploration because here you have this sample with a lot of weights, right? With the big weights. And then once you split it to 3 different samples, because you simulate an SDE, because of the stochasticity, these samples can go in different ways. And now they can explore more. And they can like actually explore different modes. So if you were propagating this sample with this weight further and further, it would just change the weight. And I mean, it can explore, but this is like one sample, right? Like if you have several samples instead of this, they can go different ways and they can explore the space, right? Yeah.
Just resampling to the same mode. That's fine.
It depends on like how you're resampling, right? Because like here the resampling, for example, like let's consider annealing. I think annealing is a good example for this because the weights here are proportional to the nabla log density. If you're like in the mode, exactly. So the weights depend on the gradients rather than like on the absolute value of your density. Yeah.
Any questions online?
No, someone just posted one.
There is one question from Benno K. You mentioned that the ITO estimator is 5 times more efficient than when you take the divergence. Am I understanding correctly that the ITO density estimator only works for SDEs, but in principle the same approach can also be applied for ODE-based approach like flow matching at the cost that is slightly higher?
Okay. Yeah. So answering this question, the crucial part of the eta density estimator is the knowledge of the score. The score, because this is what you get from the just derivations. You can get score from the flow-based models when you have when you're like, if you do flow matching with a Gaussian prior, you can reverse engineer the score. And then you can do all the same things. But the speed of the eta density estimator comes from the fact that like we don't need to backpropagate through the model. Because here, if we do the equations for ODEs, you can do the same of course thing for like a different vector field, etc., etc. But you have to estimate the divergence of the vector field, and this is a very expensive operation. In the eta density estimator, we get these things for free because we just know the score, and now the rest is just multiplications and additions. So I mean, for free compared to the forward pass of the model, of course. This is divergence of the drift, and the drift is usually linear, and yeah. Only classifier free. Presented results consider only the classifier free guidance case. In case of classical classifier based guidance, then we are interested in sampling from a product of distributions where one is a classifier and not a diffusion. Can the speaker comment on that? Okay, so yeah, I mentioned in the very end, this is not something that we considered in the work, but I mentioned in the very end that like you can put a classifier based guidance. You have to change this density in time, or you can fix this density and like add some temperature. You can do like many different tricks. We actually have a proposition on this, like some mathematical statement in the paper, how to do it like with the reward function, defined in the end of your integration. The caveat here is that you won't have this nice kind of guidance term unless you know the diffusion process. So we add these additional terms here because we assume that we know the diffusion process for the product, right? So that's what we started here. For all the models, for all the densities, we assume you can add the resampling step though. With the reward function, you can totally do this. And there is such a result in the paper. You can look it up. I think there is a reference to it in the conclusion, but in the appendix there is a reward tilted scheme. We haven't done any experiments with this, in partially because there are a lot of people doing rewards, reward optimization with sequential Monte Carlo. We try to explore something different that was unexplored before. I think that's the answer. Thank you.